Hey, and welcome to this presentation, Understanding and Interpreting Pedigrees. This is going to walk us through what pedigrees are, how we can understand them, how we use them in genetics, and indeed some actual uses of them in history. So let's jump in here. We're going to start out by first of all figuring out what a pedigree is. You may have heard the term, but what the details are does sort of matter here. So first of all, you know them as family trees, and obviously they tell you about family history. What do we know about your family or someone else's? They allow us to track genetic changes and traits through time, who back in generations previously had some disease or the like, so we use them for that. And we use them a lot also in non-human settings. Animal breeding is probably the biggest example we tend to see there. We do them with dogs, cats. Your dog, if it's purebred, may actually have its own pedigree of its family. Certainly we see it in horse racing, where millions of dollars are at stake if you have a horse with a certain pedigree. Obviously, the horse of that is a child, let's say, of a Kentucky Derby winner is worth a whole lot more than a horse that just worked on the farm its whole life. Also used in endangered species research. They're used to, for instance, tell with whales or dolphins in the ocean, you get samples and you can tell who's related to who. Jane Goodall in her work on chimps used these pedigrees extensively to figure out the social structure in different chimpanzee families. And then often used in zoos. You want to know who's related to who in endangered species research. So, for instance, you don't have close cousins maybe mating with each other in zoos. You can choose individuals who are further apart, and that helps with your managing of very small populations. Let's switch on over now and take a look at some of the symbols you'll be seeing. You won't see all of these symbols, and one thing to understand when we do pedigrees is there's a lot of flexibility in the symbols that are used. So I want you not to memorize all these, but just to get a sense of what's going on with them. So I'm going to switch down here to my laser pointer version. Okay, and this will help kind of guide us. So the first two males on these pedigrees are represented by squares, females by circles. Then historically, sometimes you don't know the sex of a person. Oh, so-and-so had a child, but that's all you know about them. They can be shown with a little diamond shape there. Next thing, this word you're probably not familiar with, proband, and you see the arrow pointing to it here. That simply means that's the person you're interested in or you're talking about, if they're the proband. Then if a circle or square is filled in black, that's a sign that they're affected by some disease, perhaps, or some genetic condition. A carrier filled in halfway. A lot of times folks don't use this, but that would be someone who is usually what we would consider heterozygous for a situation. And then sometimes you'll see females, the circles with a black dot in the middle. They're called carriers. That's another form of being heterozygous. You'll see it says X-linked. We'll understand that better later on. Don't worry about it for the moment. A diagonal slash through means the person, when the pedigree is put together, is deceased. They died. You can see if there is a line between two married people and the two slash marks there, that's a sign of divorce. The last one in the first column here, consanguineous mating, that means within bloodlines. That means within a family mating. Those make us kind of a little creeped out there, but they do happen, and so we need to record them. More on those later. Then we get up here and kind of a family of four here, where you have the husband and wife, showing with a horizontal line there, and then their two children. Okay, a daughter and a son. The oldest child is listed to the left, and then each subsequent younger child listed to the right. Then the next group here, the adoption. You can see if you're adopted into a family, such as the case with my family, you would see the husband and wife not being biologically related to the child there, the dash line, and then the kind of parentheses around it. If, let's say, a child is given up for adoption and adopted out of the family, you can see then here the, oops, that went too far. The lines are all solid there. And then you have, notice the twins down in the next series. Okay, you have monozygotic twins. These are identical twins, so they'll both be the same sex, either male and male or female and female. And they are shown here, you can see by the V coming down, and then what makes it look like the letter A with a crossbar there. Those are identical twins. And then fraternal twins, non-identical, they just share, they both come down at that angle, but they don't have a line across in the middle. And then the question mark in between them means, for some reason, you don't know if they are identical or fraternal. And that's usually, as you go back deeper in time, you don't always know those things. Some other things just to look at, on the left side, the first four you're already familiar with. Down here, if a pregnancy does not go to term, does not go all 9 months, and the child is dead, there are two ways to show that. The triangle there, the pregnancy loss, and it might have a number in it indicating the number of weeks that the pregnancy ended at. The other one is a stillbirth, which would be a circle or it could be a square with a line through it, and the number of weeks old the child was when it was born dead. That's unfortunately what a stillbirth means. And then you can see bottom line, divorced or not together. You can see here it's shown with a single line. Whether it's single or double doesn't matter. You get the idea there. And then when the family information is more limited, okay, you may know that you have a lot of kids in a family, but you may not know specific details. You could see here's a family of 8 children where you knew there were 5 boys and 3 girls. So that tells you there. Then in the last one there, if you don't know the sexes of the child, and this usually is taking us back in history where we just don't have complete information, there you could say, I would know this family had 8 children, but I don't know the makeup of the boys and girls. So that helps us there. Then a few others. Over here on the left, this kind of double box, index person, that's kind of like what you heard before, proband. Okay, male and female, we know that. Then one way of showing the age of people when the pedigree was put together. Here you could see that this would be a male who was 47 at the writing of this. Then they were born in 1970. So that would tell you a sense of when the pedigree was put together as well. Same situation over here, just for a female. Another way of showing someone's deceased, putting an X through the circle or square. You could show how old they were when they died. This person was 70 when they died. Okay. You also sometimes will see a little bit more information where the age at death and then their birth and death dates. So those are all things you can see. You're not going to see these in all pedigrees, but you're familiar with them if you see them now. So that takes care of that. And now here's an actual pedigree of a family that starts off here at the top with, let's say, Alice Murray and her husband. We know that she died. She's filled in black, so she was affected by something. We don't know what. And she died at age 52. We see her husband was not affected by this, and he has also passed away when this pedigree was made. Then we know that they had 3 children. Their eldest was Molly. She was born June 14th, 1937. She died at age 35. Oh, I'm sorry. She was diagnosed with whatever the disease here is. I'm guessing, in this case, it's a cancer diagnosis, and she died at age 40. But in the meantime, she married Robert Jones, who was born on January 22nd, 1935. They had two daughters, Julie and Margaret, and their information there. We can see Julie inherited whatever this disease is, and she was diagnosed at age 44. Moving on, the son Michael Murray, born in 1935, died at age 67. He married Joan Murray. They had two children, Mary and Sarah. Okay, Mary was diagnosed with this disease at age 40, died at age 42. And we can see her younger sister, Sarah, born in 1966, still alive according to this. And then finally, the youngest son of the original couple, Peter, not married, born in 1936, and that's what we know about him. So that, and then in the third generation down, or fourth generation, excuse me, we have Melanie, Charlotte, and Gemma, who are all females. None of them married. At the time this was put together. You'll also notice none of them being affected by whatever this particular disease is. So that's a sample. Here's a cartoonish kind of version. You can also get a sense of who's who. The proband in this case, the person this is made for, is this female here where it says me. Okay. The twin sister, ideally, I don't know if that's identical or fraternal, but they should have that V coming off that line. They have a brother that's not a twin with them. And then all the other family relationships that we'll get into in more detail later on. But this goes up to all of her four great-grandparents there. So that is the deal there. Actually, 4 of her 8 great-grandparents, because notice we don't follow her mother's line off here. So this would just be what we would call her paternal pedigree. And with this pedigree family, it's a large family, and to save some space, you'll notice that they have cut the family setup down a little bit here. So each married couple now has what I call the U shape underneath. That's the same as the line between. It just saves a little space for a big family like this, so you can fit it all on one page. And so with this large family, a couple of things just to point out. You could see that family A and family B at the bottommost generation, you have folks who are affected or filled in black there. You have the zebra pattern there, the black and white stripes. That probably indicates people who are heterozygous for the trait. You can see the bottom left person, number 1 in that generation, has the arrow, as does person number 1 in family A. So those are the people we're particularly interested in for some reason. Then you'll notice on the left side here, you have family members, a number of children, and just those numbers in to save space there. You have a child, a female, who died here. We do have several situations of the consanguineous marriages, often shown by a double connection here. So you can see these two folks are cousins. You are a cousin if you share the same grandparent. So first cousins, if you follow them both up, they share this set of grandparents. So that's the double line there. Okay. I also see this here, which indicates a consanguineous marriage. We don't know anything about her family, but presumably there would be some connection there. We come across another consanguineous setup there. And then a new symbol that you don't see before. You see these 3 females, and you see this kind of 2 lines underneath them. That means that's the end of that line. They did not have any children, and they are usually past childbearing age. So that's what that means. So that gives you a taste of the symbols there. Okay, here's another one, just another with a little bit of practice. So here on the left, you can see the number of generations there, 1, 2, and 3, often done in Roman numerals. And then within each generation numbered, 1, 2, 3. So this person would be person 1 in generation 1. This person here would be person 4 in generation 3. Very easy to pinpoint where people are that way. The one thing you really haven't seen before, here's a good case of non-identical twins. I know they're non-identical for 2 reasons. One, male and female can't be identical twins, and 2, there is no crossbar between them there. But that's the situation there. I know these 2 females in generation 1 are sisters because of this. Again, it doesn't show their parents up there for whatever reason. And then in modern times here, if you go and you do one of the online genealogy websites like Ancestry.com, genealogy.com, those sorts of things, they may have a different look to them. And this is basically the same sort of thing you're seeing before, except it's here, in this case, it's turned on its side, so the most recent person would be over here on the left, okay? And these would be his 2 parents there, their parents, and so on as you go up. So it's just twisted around a little bit. But this is how you might see a more modern version of things. So let's take a look now at how do you tell dominant versus recessive traits when you look at a pedigree. And here you can see one that has 3 generations, and how convenient that all the genotypes for trait A are listed. So you have all these here. We're going to pretend for a moment that they're not there, however. And so the question I would always ask, and I will ask of you guys, is how do you know if this trait here is dominant or recessive? Well, the way we do it is we look at all the affected individuals, all the people who are filled in black in this case, and we ask the question, do they have a parent that is also affected? Because think about it, if you have a dominant trait, if you have capital A in your genotype, you had to get it from one of your 2 parents, and that means they were affected. So as we look here, I start in the bottommost generation, in this case generation 3, and I see I have 4 affected people. So I ask for each one of them, do they have a parent who's affected? So person 5 here, the answer there is yes. For person 7, yes. Person 11, yes, they have a parent who's affected. Same for 13. And then I go to this generation, person 4, does she have a parent who's affected? Yes. And for person 6, does she? Yes. So that confirms to me that this is a dominant trait. Okay. Now with very, very small families, you could make the argument that it could work that way for dominant or recessive traits, and that is true. But for our purposes, we're going to go with this and not worry about those exceptions in very small families. And you also notice with a dominant trait, it does not skip a generation. Okay, if it were, that would be a sign it was a recessive trait. Okay, so here's a great example. This is a situation called woolly hair, where the hair grows, but it never grows very long because the shaft of the hair is very brittle, and it curls up and then it breaks off. And in this family, you can see there's a certain style to the woolly hair. You can see there's usually a part right down the middle, and this photograph isn't the best, but it looks like a lot like steel wool or a nubby sort of texture to it. So like this young man, I think, has it. I think his father has just normal hair, and it's combed over in the style of that day. The mother here, she definitely has it. It's not very long. This boy here might have it. This boy looks normal to me. This boy seems normal, as does this other one. So I'd say certainly the mother, the oldest son, maybe this, what I'll call a middle son. And this, I'm guessing the oldest daughter, maybe. She has a bow in her hair, so it's hard to tell. But anyway, you get the idea. And here's the pedigree of a large Norwegian family with this trait. Okay, and you can see a number of things. 5 generations, lots and lots of people. You'll notice the diagonal lines. That's just a way of, sometimes you have to shift people over to fit properly. But my first question is going to be, is this a dominant trait or a recessive trait? Well, you don't know offhand, other than the previous slide told you so. But so let's start. We start at generation 5, and I basically look, and everyone in generation 5 has a parent who's affected. Then I go up to generation 4, do the same thing, and I go across, and you can follow me. Every single one has a parent who's affected. Generation 3 going up to generation 2, same thing. They all wind up tracing back to this one woman who, is apparently the start of it in this family. So this is indeed a dominant trait. Okay. Some other things that might stand out for you here. You'll notice that this initial woman, she had 2 husbands. I don't know the details of it, but my guess is one of them died, and she remarried. Okay. It does not, that's why it doesn't show divorce there. Okay. You'll also see, here we have 3 sisters. And then you go down and you see 3 diamond shapes with question marks. 2 things. The diamond shapes with question marks, my guess is whoever put this together didn't have any useful information other than, yes, all 3 of those daughters had children, but they didn't know anything about who they were. Maybe they moved away, and so that's the deal there. And they may not have included their spouses just to save space. Anyone's guess on that. You see a couple in generation 2. The diamond shapes, again, these may have been people that just you had incomplete history on. So you know that they existed, but you may not have even known a name. So you don't know, you may have heard that this couple had 5 children. And so, and the only one you knew about is this son who then marries and so on. So that's the situation there. Dominant trait, everyone who's has it has a parent who's affected. And now when we look at a recessive trait, this is a situation where these do skip generations or appear to pop up out of the blue, which if you look here down to generation 4, there was no sign of this ever happening in this family, and then it popped up there, persons 2 and 4 in generation 4. Okay, and this is a case where I'm going to start off, and I'm going to leave that, and I'm going to say, do those people in generation 4 have parents who were affected? And you can see I go up, and the parents there are generation 3, persons 5 and 6. They're not affected, so I know this can't be dominant. It fails that test right away. So this is a recessive trait, and recessive traits often pop up from parents who are heterozygous, but who may not have known they are. And if this were a recessive trait and both parents were affected, then all of their children would be affected. That's something that often jumps up as a way of being real obvious to us. And here you can see, you can try and fill in the genotypes of everybody, which is a little bit harder with these recessive traits. You can tell some folks are heterozygous. Some folks you just can't quite tell. They show the dominant trait, so they're, in this case, big A, something else, but it's not totally clear. Anyone who's affected with a recessive trait has to be little a in this case. So take a look here. This is for sadly, a fatal disease called cystic fibrosis. that is where you cannot get mucus up out of your lungs. The little cilia hairs that normally move mucus up out of your lungs so you can swallow it, they don't work as well, and because your mucus is made and it's much, much thicker. If you've ever gotten a chest cold where you have lots of mucus in your chest, imagine it being like that, but even worse. And these children usually wind up dying as children from a series of infections in their lungs related to this excess of mucus. They also will get intestinal problems due to the intestinal mucus blocking their digestive system. A very unpleasant situation, and sadly there is no cure for it. There is some genetic treatment that is hopefully being developed, but we'll talk more about that down the road. So as you look here, is this a dominant or a recessive trait? And so I always start out asking the question, is it dominant? And so I start down at my bottommost generation, in this case, generation 4. I have 2 people affected. Do they have parents who are affected? And I see neither parent affected. So right away, that tells me this is recessive. I see that again up here in generation 2. So it skips generations, and I have people without affected parents. So this is definitely a recessive trait there, and that's the situation there. Okay, let's give this one a shot now, where you see lots of affected people here on the right side. So I ask, is this a dominant trait? Well, let me start here. I got these 3 siblings. They are all affected. Oh, they have both parents who are affected. That suggests to me this might be recessive, but so far it still fits my dominant trait idea. Do people 3 and 4 have a parent who's affected? Yes. So far on the right side here, it looks like it's dominant. And then I get down to person 3, and they don't have a parent who's affected. And so that tells me, boom, right off that we're dealing with a recessive trait. Let's try this one. So here, if you take a moment to look at things, you have 5 affected people in the bottommost generation there. They all have their mother affected. The mother and her 2 siblings, their mother was affected. So yeah, so this one looks like it is dominant as well. So that would be a dominant trait there. And here we have a large family, and you can see a lot of them have died. You may wonder, some of these say AA, BC, AA. I do not know in this particular case what those refer to. They don't influence anything we're doing. And so let's take a look here and see, is it dominant? These have parents. These have this parent, this parent. That line, by the way, should be connected. Okay, that just didn't show up in the scan. Yes, yes. So everyone I'm looking at here, it's looking dominant. Then I'm going to come over here on the right side. Okay. This is looking dominant. All of that looking dominant. Yep. So this one looks dominant to me, and indeed, that is the overall assessment. Okay. Here's one. This one looks maybe a little bit different. Okay. So you look here and you notice that you have some folks with parents who are affected, but you have several who are not. And all it takes is one to not have a parent who's affected. And so that tells you, oh, and by the way, there should be a line right here. Okay. So these folks are children of these. Doesn't affect the end result that this is a recessive trait. But something else, the reason it looks funny is you'll notice every person in this is male. Okay. And that seems a bit odd. All of the others, if you were to go back in this video and look, they have a fairly even male-female split, as we would expect. But this is obviously something that impacts, for this pedigree, only males. And that is often a sign of this new type of problem we're going to deal with called a sex-linked trait, where the gene that causes it is actually on the X chromosome. And if you remember, the X chromosome, women have 2, so they inherit it just like every other trait with 2 copies of it. But males only get 1 copy of the X chromosome because we have the Y chromosome, which is a smaller chromosome that doesn't have all the genes of the X. So if you have only 1 copy of the gene and it's recessive, males will show that trait, whereas much less common amongst women because they have 2 copies of the X, and thus they would require 2 copies. And that gets us here to the idea of a particular trait that has a connection with all 4 of these images here, ranging from George Washington and the American Revolution to Adolf Hitler to Queen Elizabeth II, her husband Prince Philip, and Vladimir Putin of Russia. So a very, very interesting connection here that I want to relate